optimization approach. So let me say a few words about this packing and covering problems. So there's a very nice reference from John Conway, who is the famous mathematician who died last year. So it's about sphere packings, and it's also about coverings and related problems like the kissing problems for spheres. So the kind of problem that they consider, that was traditionally considered, is the problem of packing and covering in the whole space, in any dimension. So, and these two type of problem, packing and coverings, they are kind of dual in a certain sense. They have a lot of similar properties. So you can see the packing problem would be this problem with the figure on the left. You want to pack the spheres or the disk in dimension 2 so that they have the highest density possible. Okay. So you want the space between them, the empty space, to be as small as possible. And in 2D, the typical solutions, they are given by lattices. So lattice is a kind of regular discrete grid, if you want. So the hexagonal lattice gives the solution for the packing in 2D. And if you look at the covering problem on the right, there's two examples here. There's one. So the goal of the covering is that you want to cover the whole space, but you want to have the thinnest, they call this I think the thinnest covering, which means you want as little intersections between the balls or the disk as possible. Okay. So for instance, you can see clearly in this configuration that the configuration on top is worse than the configuration at the bottom here, because you have more intersections between the circle. So this configuration on top is a square lattice, and the configuration at the bottom is an hexagonal lattice. So you can see the position of the points, and you see the intersection, they are smaller here. And the famous solutions, these problems are very, very old, like they are 300-400 years old. For instance, there was the conjecture of Kepler for the best packing in 3D. You know, this pyramidal packing of oranges, for instance, which was solved around the year 2000 by Thomas Hales, and he has this very complicated proof that they were not able to say if it was correct or not. So, but now it's more or less admitted that the proof is correct. And there's also some nice results for packing in 8 dimension from 2016. So it was a breakthrough. But of course, the configuration of the lattices in higher dimension, they get much more complicated because you have many options. Already in 3D, you have many possibilities of packing, of regular packings, right? Okay, so it's just an introduction to the topic. But what I'm looking at in this talk is the covering of subsets of R2. So not the whole plane. So it's really different because you won't have solutions in the form of lattices. So you can really have any type of geometric configuration of the balls. Is going to depend a lot on the shape of A. Okay. So first, I'm showing the mathematical formulation that we use to solve these problems.
Antoine, just a question, small question. So when you were speaking of these lattice structure, it's for the whole space, or for it's also true for some subsets of the whole space?
There's a lot of literature, and they also consider the covering of subsets with lattices, but usually it's some very specific shapes, like for instance, covering of a square, covering of a triangle, covering of a ball, these kind of shapes. And then then you can try to cover with a small lattice, the same type of configuration. But here we're really trying to cover any kind of shape, A, okay? So that's the main difference. So it's more applied, if you want, in a way, because you can really consider some applied problems where the shape A can be anything and you want to cover it. Imagine, for instance, the coverage of a satellite. You have several satellites and they can cover some specific region, and you want to cover the entire region A without any gaps, but this region A could have a very irregular contour, for instance. But there's a relation between with the lattice. I will talk about this when I show some numerical results. So the lattice is a very important structure for the discovering problems. That answers your question?
Yes, thank you.
Okay, so the shape that we use to cover A is a union of balls, but since we are in 2D, it's a union of disks, in fact. Okay, so you have M disks, which are called B of X, I, and R. And the centers, they are called XA, and so I use this boldface X, which is like a vector of the positions of the center. And the variable for the optimization is the set of the centers, X, and the radius. So the point here is that all the disks, they have the same radius, okay? But you could also define problems where there's different radii, but here we consider the case, which is quite common, where all the disks, they have the same radius. So you can have a formulation of the optimization problem as a minimization problem. So you want to minimize the radius with the constraint that this function g is equals always to 0. And this function g is the volume of the A minus the volume of the intersection of A and the set omega. So you can see, you can check that g is equal to 0 is the same as, is equivalent to A is included in omega. Of course, you have the problem that you use the volume. So this inclusion is only up to a set of 0 measure. So this is the inconvenient of considering this this kind of function, but on the other hand, it allows for a quite general approach. Okay, but that means if you have a set of 0 measure, then it's more, you won't be able to cover this with this kind of approach, like if you have a line in 2D, for instance. Okay, so the problem becomes
another question. I'm more used to thinking of this optimization problem where you fix the radius and try to minimize the number of points, but this seems to be in a different way, no? Because you're trying to minimize the radius, and what is fixed, M is fixed, the number of points.
Yeah, the number of centers, the number of balls is fixed. So
Okay.
you have a fixed number of disks, okay? And the only variable that you can change is the radius of the disk and the position.
Yeah, okay.
And so you want to find the smallest disk that such that the union of this disk is covering the shapes, okay? I'm going to show many pictures, and I think it's easier to understand. But the point is that this minimization problem is a finite dimensional problem because you only have 2 m+1 variables. Okay. So let me show you a picture, then I think it's much easier to understand. So the shape A in this example is the orange shape. So it's like this this polygon here. And you have like 10 disks, I'm not sure, 5, yes, 10. So you have 10 disks, and your shape omega is just the union of these disks, okay? And here on the sub figure B, I'm showing the intersection of omega with the polygon. So this gray region, okay? So you can see here, you have the parts which are not covered are the orange parts. So the goal is that there's no more orange parts at the end of the optimization, okay? And at the same time, you want the smallest radius of this disk as possible. So one important quantity for the optimization we'll see later is the red arcs here. So that's why I emphasize these ones. And I'm going to define one important notation is this calligraph AI, which is the intersection of one of these balls, for instance, this one, with the boundary of the set omega. So, for instance,
one more thing. Your screen is not visible completely. It means bottom side of your screen is not. For example, the circles below is not visible. Is it because you did not scroll down or something?
You mean in the figure B?
Yeah, in the figure, no, in this whole figure, the below part of the figures are not visible.
In the whole talk, I think I can see the bottom part of the.
So you cannot read the text here for the figure.
Or the
caption.
bottom part of the figure. Also.
Yeah, the bottom part of the figures are not visible. In all the slides, the bottom part is not visible.
Okay. And if I do this, can you see, for instance?
Yes. But Lucas can suggest you better. He has an opinion that you can the visibility can be better. Lucas was suggesting something. Lucas, can you please write down in the message? Lucas has some opinion for making the look better because it looks like the presentation mode is not working, which you are in.
Professor Antoine?
Yeah, Lucas, can you please suggest how can he?
Did you try to go in the view option in the left? Yes.
Yeah, I tried I was in presentation.
Yeah, in full screen?
But presentation doesn't work, you say, no?
No.
Okay, let me try the full screen then. Or is it?
No, same.
Yeah, now it's better.
Now it's better, but yeah.
Like this is better?
Yeah,
yes.
And like, Professor Xavier is saying the mouse does not show what he means. I don't know, Xavier, what you are saying? I didn't get it. Mouse does not show what.
No, well, I don't know. The mouse you were showing figure B, for example, and the mouse was not on figure B, so I have a doubt. Maybe that works.
For instance, now my mouse is on figure B. Is okay?
Yes. Now
yes.
It is.
Okay. Yes. Now yes.
Now it's okay.
Now yes. Yeah. Perfect. Sorry. Please continue. Yeah.
Okay. So. So this set calligraph AI is important. For instance, let's say this ball is B1. So the calligraph A1 would be this arc and this arc. Okay. For instance, if this one is the ball B2, then the calligraph A2 would be this arc and this one. Okay. So the calligraph AI is just a union of arcs, if you want. Okay, all the arcs which are on the boundary of the set omega. Okay, so this caption says that most of these sets AI, they contain 2 or 3 arcs. Okay, in this example. Okay, let me just before I start showing the formula, let me just show you some important notations. Well, there's the scalar product with the dots. This is the usual thing. There's the tensor product. Maybe some people are used to it. Maybe some other people not. So it's like you can see this as a matrix product of two vectors x and y transpose. So the tensor product of x and y is a matrix. If the vectors are size n, then the matrix is n times n. So the ball, I already explained the notation. Then there's the normal vectors to some set S, which I call nu S. There's the tangent vector to S, and it's pointing always counterclockwise. This is important. And also I use the notation nu I for the normal vector to the ball and tau I for the tangent vector to the ball. So just to simplify. And another important notation is the nu minus I. It's basically the same as nu S, but for intersection point between the boundary of a set S and the ball. Okay, I forgot it should be the boundary of the ball, not just the ball, okay? So this notation is just to emphasize that this, because at the intersection point, you have two normal vectors. You have one for the ball and one for the set S. So this nu minus I is just to explain that it's not the normal vector to the ball, but to the set which is intersecting the ball, okay? I need this notation because afterward I'm going to use this nu minus I a lot. So here's an example of these notations. For instance, if you have two balls, for instance, the set AI is going to be these two arcs in red here. And you can see at the point V, you have the normal vector to the ball BI. And the nu minus I is the normal vector to the set A. So the set A here is a square. So the nu minus I is just the normal vector to this square. And if you have the intersection of two balls, you also have this this notion of nu I and nu minus I. For instance, here, the nu I would be normal to this disk, and the nu minus I would be the normal vector to the other disk, okay? Okay, so let me show you now the algorithms that we use to solve this problem. They rely on the first and the second derivative of G. And the way to compute what is interesting is how we compute these derivatives. We use a shape.
Sorry, Antoine, can you just show me what your function G is once again, please?
So the G is basically just I mean, I call it volume because it would be general for dimension D, but here it's really like an area. So if you look at this picture, the G is basically the volume of the orange part.
Okay.
Because you want this G equal to 0. So you don't want any orange part because you want to cover completely the polygon. Okay.
Okay.
So it's a simple, it's just the integral of 1 basically. So it's a simple shape function. So to compute the derivatives of G, we use techniques of shape calculus. So here I wrote some people, some well-known people in this this topic. Of course, a lot of French people, as you can imagine. So the gradient of G, it's relatively simple compared to the second order derivative that I'm going to show afterwards. So it's basically for the first terms of the gradient of G, they are the derivatives with respect to the centers. When you make perturbations of the center, for instance, perturbation of the center of the first ball, then you get an integral over A1 of nu 1. And all the other ones, they are the same integral over the. So remember that this AI is a union of arcs, okay? And the last one is the derivative with respect to the radius. So this time is an integral on the entire boundary of omega inside the domain A, okay? Later, I will explain a bit more how to get these formulas. And the Hessian of G is more complicated because you have to consider many different cases. So it's a matrix. It's a block matrix. So you have, for instance, this block gradient to X, which is a matrix 2M by 2M. This gradient to XR, it's like a vector. This one is just the transpose. And the last one, the gradient to R, is just a scalar because the radius is a scalar, right? So let me show you the formulas. I'm not going to explain in a lot of detail this formula because it would take a long time, but I just want to explain a few of the main ideas. So basically, what you need to describe the terms of the Hessian is the set of the arcs on the circles, and you need to represent these arcs by the extreme points of the arcs. So each arc, we represent it with a vector VW. So V is the entry point of the arc, and W is the exit point of the arc. If you think in a counterclockwise orientation, all right? Well, we set this. So AI is really a set of arcs, okay? And AI is just the union of the arcs, so it's slightly different. And then, for instance, the second derivative of G, it's all geometric terms, right? So it looks complicated, but in fact, the quantities, they are not so complicated inside. So for instance, this gradient involves the perimeter of the boundary of omega intersected with the set A divided by the radius. And then you have these sums over all the arcs. And you see in these sums, you have this new I and this new minus I. So it all depends on the angles between the disks, the way the disk intersects at the intersection point. So it all depends of the angles between the normal vectors at the intersection points in this sum. And this notation is like the notation that is like an extension of the notation that you can use for integration by parts. So it's just the value of this quantity. It's defined here. So it would be a phi of z between v and w is the phi of w minus the phi of v. So it works a bit like integration by parts. Because in fact, we are doing sort of integration by parts on the arcs to get these formulas. And the L of z is basically something which is equal to 1 or 0. Is the indices of the intersection between the balls, or between the circles, in fact. So when you have a circle BI, then you need to check which other circles are intersecting it, and then you will put the indices of the intersecting disk inside this L of z. Okay, so this norm of L of z is just equal to 0 or to 1, depending on the case. But as I said, it's difficult to understand these formulas like this in this talk. But the important part is to understand that all of these are simple geometric quantities that you can compute in numerical algorithms. Okay. So then you have the second derivative of G with respect to the centers, when you have the same center, so it's the diagonal terms of the matrix. And it depends also on the normal vectors and the tangent vectors. You integrate over the arcs, and you have the same kind of quantities here, which are values at the extremities of the arcs, okay? You can see that the same kind of quantities always appears like this nu minus I scalar tau I is similar to this case here. You have nu minus I scalar tau I. It's always a question of angles between the normal vectors. Okay, this term, maybe I can just keep the explanation because it's a bit more technical, but it's the off-diagonal blocks of this matrix. This Hessian matrix. You can see here you have this tensor product, so it's a little 2x2 matrix. That's why you have this tensor product here. And then you have the final formula is for the mixed derivative between if you have a derivative with respect to perturbation of the center and perturbation of the radius. But all these formulas, they look similar, but there's some small differences between them. But you always have this integral over the arcs of the normal vectors and this kind of terms with the sum over the extremities. Okay. Let me explain now. I think what is the most interesting part is how we get these formulas. I'm going to explain not the technical details of the calculation, but the main idea is to get these formulas. So here I'm showing a configuration with 5 disks. So it's m is equal to 5. And I'm going to make a small perturbation of 2 disks here. So here you have a disk with the center xi, here with the center xj, and I make a small perturbation of this center and this center here. So you can see the shape is changing a little bit. And what I need to do is to find a transformation which is invertible. I need the invertibility to compute the derivatives. Basically, I need this transformation to do a change of variables in the integrals and then to compute the derivatives with respect to the small t. So the question is, how can I build this transformation capital T, which depends on the small t, and the small t is just a pseudo time used for the perturbations, right? So in these works, we are building this capital T in sort of explicitly somehow. I'm going to explain how. So you can see the result for the shape omega. So omega is the union of this ball, so it's this gray region, and you can see the change of the shape of omega globally when you make this perturbation of the balls. So what I need is a transformation capital T, which transforms omega into the set omega of x plus t delta x. Okay, and this is I need a transformation when I have a perturbation of the centers, but I also need perturbation when I have a transformation t, which corresponds to the perturbation of the radius. So in this example, I do a perturbation of all the radius at the same time. So you can see each of these disks is increased as an increasing radius in this example. So that's why you can see here globally the shape, the reference shape omega, and here you have the transform shape omega. So the main difficulty to build this capital T is the fact that the shape omega is not regular because you have these intersection points. And in addition, I didn't draw, but you also have the intersection with the set A. So it's also a point where this intersection is not, where the shape is not regular. Okay, so now I'm going to explain how can we build this mapping capital T. So what I need is that these mappings are Bi-Lipschitz, so which means the mapping is Lipschitz, and also the inverse mapping is also Lipschitz. So, and it needs to map the shape omega onto the perturbed shaped omega of x plus t delta x, and another mapping for the radius perturbation. So how do we do this? The first observation is that the boundary of omega contains singular points, which are the circle intersection, and regular points. So if you look at this picture, the singular points is the circle intersection, like this point, this one, this point, etc. And the regular point is a point, for instance, here. These are regular points. And the point is that the motion of the singular point is fully determined by the perturbation of the center or of the radius. I think This is relatively easy to understand because if you consider, for instance, the intersection of two circles and the radius or the centers are moving, then it's clear that you can describe explicitly the motion of these intersections, right? So you can do this, for instance, by using the implicit function theorem, or if it's just two circles, you could write an explicit formula for the motion of these points. So this is exactly what we do. We're writing the equation for the explicit motion of these intersection points, and using the implicit function theorem, and then so we determine explicitly the motion of these points. But then the interesting part is that the motion of the regular point is underdetermined. So that means there's one direction of the perturbation TT which is prescribed. For instance, the fact that the perturbation T, the transformation T needs to correspond to the perturbation. So that means the points, they need to move with the perturbation T delta XA, for instance. But the other direction, the orthogonal direction, can be chosen freely. So I wrote this with quotes because it's not completely free. There are some constraints, but there's some also a certain degree of freedom to choose the perturbation. So basically, we are free to choose the orthogonal direction of TT at the regular points, but we need to satisfy a few constraints. So the capital T must be Bi-Lipschitz. The value of T is prescribed at the singular points, and we need to, the mapping capital T need to map the set omega intersected with A to the set omega of X plus T delta X, okay? And then we use the fact that d omega is a union of arcs. So this is quite practical because we can use local polar coordinates on each of the boundary of the disks. And in this way, we can do some kind of, how can I say this, interpolation of the values using polar coordinates or at the regular points. So if you want the value at the singular point is prescribed, and we interpolate these values at the regular points using polar coordinates. So this is quite convenient then that we use disk. And if we were not using disk, this would be much more difficult. And I'm thinking about this kind of extension, but I haven't found the solution to this yet. And then once in this way, we can define the transformation T everywhere in the domain, everywhere on the boundary, and then we can extend in a Bi-Lipschitz way everywhere inside the domain. So this, we don't need an explicit extension. We do this just using some general extension, okay? But the advantage is that we have really an explicit construction on the arcs, and this is quite useful afterwards to compute the derivatives of this function G. Okay, so I just gave the general idea of how to build this capital T. I'm not showing all the details, it's all in the paper, but really the construction in the details is a bit technical, but basically these are the main ideas, okay? Okay, so now I'm going to show how to use this to compute the derivatives of G. So it's relatively simple for the first derivative. So once you have built this mapping capital T, which maps this set omega intersection with A to the set omega with the radius R, with the perturbed radius R plus T delta R intersection with A. And then we use a change of variables. So we write G as an integral. So it's like the volume of A, which is a constant, minus the integral on the capital T applied to omega intersection with A. And then we do the change of variable, and we get an integral on omega intersection with A. So this is the usual thing that we do in shape optimization. It's all change of variables, basically. And then we get a quantity that depends on t inside the integral, and then we can compute the derivative. So it's well known that the derivative of this term, the determinant of this Jacobian, right, from the change of variable, it gives a divergence of v, where v is the derivative of this transformation capital T. And then you can use a divergence theorem, and then you get an integral on the boundary of this v scalar nu. This is just the divergence theorem. Then you can show that this v scalar nu is equal to the perturbation of the radius, which is called delta r. So the reason for this is just because we have an explicit construction of this capital T, and then you can just do the calculation, compute the derivative, and you're going to see that this v scalar nu is equal to delta r. So it's logical in a way, because the velocity of the perturbation is just the perturbation in the normal direction when you make a perturbation of the radius, right? And so that's how you end up with the derivative of the area, which has a function of the perturbation delta r. Okay, so I'm not going to show the other calculation, but it works in a similar way. And so this first point, I said already that this property v scalar nu is equal to delta r on the boundary. It comes from the explicit construction of the capital T on the boundary. For center perturbations and for second order derivatives, it works with the same principle. It's just for the second order derivative is a bit more complicated, because you need to use some tangential divergence theorem, but the principles are similar. So basically, the main task for to compute each of these derivatives is to build the appropriate transformation capital T for each type of perturbation. But basically, you can gather many cases together, and you only need to build two types of perturbation capital T to compute the second derivative. Okay, basically just perturbation of the centers and perturbation of the radius, and you can compute all the derivatives. Let me see how much time. Okay, maybe I have still some 15 minutes, I guess.
Yeah. Yes,
okay.
yes, 15 minutes. Yes.
Okay, so soon I'm going to show some numerical results. But first, there's something important I need to discuss, is the question of the regularity assumption that we need to do all these calculations. So I didn't talk about this yet, because I just wanted to show how to do the calculation. But all these derivatives, they were obtained assuming that this points x, which is the vector of all the centers, and the r, they are non-degenerate. And we said that these points are non-degenerate when they satisfy these two assumptions. So the first assumption is that the centers, basically, you can summarize like this: the balls, they cannot be tangents, and they cannot have exactly the same centers. Okay, and also this other condition is that you cannot have three disks which intersect exactly at the same point. Okay, like I will show some pictures afterward. And the second assumption is that the sets omega and R, A, they are compatible. So there's a precise mathematical definition, but I'm just going to show a picture to explain what this means. And the idea of this assumption is that it avoids all the many singular cases. And basically, it's a kind of question of topology. That means what you need is that the structure of the arcs on the boundary of your domain stays the same when you make a small perturbation. So it's not really, I mean, I'm not a topologist, so I don't want to say something really stupid about topology, but if you want basically you want that the number of arcs stays the same, and that you have mappings between the arcs when you make a small perturbation. And if you don't satisfy these assumptions, then you have a problem. For instance, imagine if your two disks, they are tangent. If they merge or if they separate, then you will have a different sets of arcs. So let me show you with pictures how this works. I think it's easier to understand. So the compatibility basically is that here, if you have a square and a disk, in the first case A and case B, the square and the disk are compatible. It's not compatible, for instance, when the disk is tangent to the shape or it touches an irregular point, this kind of situation. So there's some precise description, but you can summarize basically like this. The two shapes cannot be tangent, or they cannot intersect at irregular points, okay? And there's some other examples of degenerate case. So you have the case of two tangent disks, so you don't want this kind of situation. But in fact, it's not that bad in the numerical results, and we have analyzed using asymptotic analysis this kind of cases, and we can show that in fact the first order derivative exists in this kind of case, which is good, and the second order derivative does not exist. It's going to be discontinuous or even diverge. So, but you can see the problem when you have two tangent disks is that you have two different type of situation depending on the perturbation, right? If the two disks go far away from each other, then you have two disks, but if it goes in the other direction, then they merge, and you have a different decomposition into arcs of the boundary. So, but you can show that the first derivative exists in this case because in fact it's equal to 0. In the two directions, it's equal to 0. It's because the area of the intersection is growing very, very slowly when you have an intersection of the two tangent disks. Another interesting degenerate case is the case of three disks. So this situation also is excluded by the assumption because the three circles, they intersect at one point, okay? And you have two different cases. You can see if the three disks get away from each other, then you have all appearing here. But if they get closer to each other, then you have an intersection of the three disks here. And in fact, it's funny because this shape is famous. It's called the hollow triangle, and you can do some asymptotic analysis, and you can also show that even in the singular case, the first derivative is equal to 0. So in fact, the function g is differentiable at least just once in this situation, but it's not twice differentiable. In this case, the second derivative is discontinuous. So we have analyzed some singular cases, and we have studied many different cases using asymptotic analysis. So you can analyze the differentiability in these cases, but you need to use a different technique because you cannot have this mapping which is invertible between the shapes in this singular case. But you can prove some interesting results like Gatto semi-differentiability of the components of the gradient in the case of the second derivative. Okay, so now I'm going to finish with some numerical results. Maybe I will go quickly on the results because I think I have, what, 5 minutes left or more? 5 to 10 minutes, maybe.
Yeah, you have something like 5 minutes. Yes.
Yeah. So, okay, so the way we solve this numerically, we use this for these formulas of the gradient and the Hessian for a numerical algorithm is that we apply, we use a augmented Lagrangian method. So there's a software which was developed by by my colleague Ernesto, who is working on this on these papers, and his colleagues from Campinas. So Campinas is a big city close to São Paulo, and there's a very strong group of optimization there. And they have developed a well-known method which is called AlgenCan. So it's like a software that you can use to solve optimization, a certain type of optimization problem. So this problem fits quite well in this framework of AlgenCan. And so we can just feed the AlgenCan with the first and the second derivative, and it's going to give the solution, right? So first, we have developed two different types of algorithm. The first algorithm is for general shapes A, and the second algorithm is for specific shapes A, which are in the form of polygons, if you want. So the augmented Lagrangian, well, I'm not going to explain the details, but it works in this way. You define the Lagrangian, which is composed of the cost function that you want to minimize. This would be just the radius, this function f. And then you have this penalization of the constraints. And then you alternate between minimizing the Lagrangian and updating the Lagrange multiplier. And the Lagrange multiplier is for the constraint, and some penalty parameter, which is called rho here. So this penalty parameter is going to increase during the iteration, so to enforce the constraint g is equal to 0. Okay. So this is a well-known approach for solving optimization problem with constraints. Okay, so here's some results for the covering problems. So this is the first algorithm that we developed for general shapes. So you can see here each column corresponds to the covering of a specific shapes. So you get some interesting regular coverings. For instance, in the case of these rings, you can really see the regularity of the covering, or this also for the half ring. Here the case of the peaked star is more difficult, and you can see that it's very difficult to cover the peak of the star because these regions, they are very thin. So from the point of view of the cost function, which is a function of area, this function doesn't see these regions because they are really thin. So it's almost like a set of zero measure. So you really need a very fine discretization of the sets to get a good covering of these regions. Okay. Okay, so we have in the paper we show many different type of coverings, so it works quite well. But after that, I'm going to show the other algorithm where we can cover with many more balls. Here in this first algorithm, we cannot have too many balls because otherwise from the numerical point of view, it becomes very expensive. So here at best, we have some 15 balls, but in the other algorithm, we can have much more, we can cover with much more disk, and we can have a much more accurate covering. Okay, maybe I will skip this performance metric because there's not enough time, but basically discusses the idea of the algorithm is that we use a multistart strategy. So we use a random initialization, and we try 100 different random initialization. This allows you to find so it's a way to explore the space for the minimization and to have more chances to obtain a global minimum. Okay. We made different tests in this paper. This is a test where we check the solution depending on the size of the discretization. So you can see when the size of the discretization is too high, then the covering is really bad, like in this first example. But h is equal to 0.1 is really too large, And you can see for h equal to 10 minus 2 already, the covering of this shape is already quite good, although it's not perfect. You can see some small problems here. But for the peak star, you really need a fine discretization to catch these little peaks here. We also tried the algorithm on some singular cases, and it works well. Although it's not covered by the theory, but the algorithm is able to find the best solution for the covering. So here we covered just 2 disks using 2 disks. So even though the derivative is not covered by the theory, the algorithm is working in this case. Okay, so let me finish quickly with the second algorithm. So the idea of the first algorithm is that we only use the first and second derivative, but the A can have any shape. And in the second algorithm, the A must be the union of convex polygons. So it still gives you a lot of freedom because you can really have you can approximate sort of any shapes with a union of convex polygons. And what is really nice with this second algorithm is that you can use the first and the second algorithm, and you can compute everything analytically, and this gives a very fast and accurate algorithm. Okay, so maybe I don't think I will have time to explain in detail this algorithm. So I'm not going to explain all the notations, but basically the idea is that you can, if you look at this picture, you can compute analytically the intersections of these disks with the boundary of the polygons. So that means you have analytic representation of the intersections and also of the arcs and of the edges. So that means all these quantities you can compute analytically. So let me show you the one simple example. So this Sij is basically one of these gray objects. So it's like it's the intersection basically of a ball with a Voronoi cell here, and so this S, one of these Sij would be this one, this would be another one, and so on. And you can see that the boundary of this Sij are just segments, straight lines, or arcs. Okay. So when you want to compute the volume of this region, you can just use Green's theorem, and you get a completely analytical expression for this volume. Because it's just you can just because you have an analytical representation of the edges and of the arcs, so you can just compute this analytically. That means numerically you can use these analytic formulas and you get a very fast and accurate calculation. Okay, and all these formulas that I showed before of the gradient G and gradient 2 of G, they can be computed in this way analytically. So it gives you some long expression, but apart from this, it's you can implement this and it's really fast. And also here you can compute the complexity of this algorithm, so it depends on the number of sides of these polygons here. So it's of the order m log m, and here you have a quantity m times a constant, which is the number of sides of A of J. So let me just finish with some example. For instance, we did the covering of the Americas here. So this is a sketch of America that we took from another paper about covering. So you can divide this into a union of polygons, convex polygons. So this, I think here, 34 convex polygons here. And then you see different type of coverings. Okay, so, And the interesting part is because this method is much faster than the first algorithm, you can really have a high number of disks for the covering. You can have some really small radius. And I think what is very interesting is that when the number of disks it becomes large, and you really start to see this lattice structure, which is logical because when the radius becomes small, you become closer to like covering of the entire space. So you can really see this lattice structure with the hexagonal structure, but close to the boundary, of course, it's a bit different because you have the really irregular structure of the boundary. Okay, so we try different shapes, and it works really well. You have a very accurate representation here, and here the goal was to try a shape really with some little spikes. Okay, so I think I will just finish with the conclusion here. I think it was a bit long in the end with these images. So the conclusion of these works is that so basically there's two works. There's the first one, which is published recently in SIAM Journal on Scientific Computing, which is for the algorithm 1, okay, where we have any shape, but we only use the first derivative. And now we just finish another work that we put on arXiv, where we use the second order method. So it's really like a Newton method, so it's fast and it's very accurate, but it's a little bit more limited because you only have this union of polygons, right? So it seems we have explored really this problem completely somehow, because also we have computed the second derivative, and we saw that the assumptions there, they seem to be really sharp. You cannot weaken them, otherwise you cannot compute the second order derivative. And now we are looking at extension of this approach. So one interesting extension would be to extend this problem to a problem with PDEs. Because in shape optimization, we often consider some PDE constraint. In this problem, there was no PDE constraint, but the ideas would be similar. So the construction of the perturbation T is there's no difference if you consider some PDEs. And an obvious extension would be to 3D, but then the construction of the capital T needs to be different. So I don't know yet. I have some ideas, but I'm not sure yet how to do this exactly, because you cannot use anymore the polar coordinates, so it's more difficult. And then there's the question of the arbitrary shapes instead of balls, and this is also more difficult because you need to find another way to build this capital T, okay? But I think looking at it in a general way, I think it's a really interesting class of problems in shape optimization. The way I see it is a different type, is a new class of problems in shape optimization where your shapes, there are unions or intersections of small simple shapes, okay? And the difficulty is that you get non-smooth boundaries, and then you need to use some non-smooth shape optimization techniques. So there's really, I think there's a lot of interesting stuff to explore in this direction. Okay, so thanks for your attention, and I hope I was not too long. A bit more.
Thanks, Antoine. As usual, I was expecting this. A very interesting lecture. Thank you very much.
Thanks.
Thank you.
So we got the clap.
See,
Thank
it's
you.
a clap. It's a virtual clap.
It's great.
Entonces, si alguien tiene pregunta, duda, comentario, algo.
I have some, but if anybody else wants,
very fast.
Or we can talk in private also. It's okay.
Yeah. So maybe Lucas will be joining Antoine soon for the proposed doc, hopefully.
Yeah.
Yeah, Rajesh, please.
Yeah, no, my question is like, so it's very nice from a numerical point of view, but I would think that for some kind of irregular figures, even like these pointed stars or these things, you would like one would be interested in using different balls of different radius, not just one radius. So maybe uh, it can be adapted, no, your techniques to.
For balls of different radius, there's no problem. It's almost immediate look because in fact in the first paper we wrote the formula for different radius. Basically, the difference is that you get you have more variables. So instead of just the R, you have like a vector of R. And do you see now the slide?
Yes.
So the derivative with respect to the R is this one, okay? So there's only one term because there's only one R, but if you have a vector of R, then you get here many different terms, and instead of having an integral on the entire boundary, you're going to get an integral just on one ball for each Ri, let's say. But I think the formula is just basically the same. It's just the integral over AI of dz, dz, and the same for each radius. But for the second derivative, of course, it's going to be more complicated, yes.
Yeah.
But the principle is very similar, so
yeah.
So it's not a difficult extension of the method. What is much more difficult is the case where you have different shapes and not just balls.
Yeah. And two more questions. So I didn't know and I didn't understand much the second algorithm, but why is it necessary to consider it's a convex? It's a union of convex polytopes or poly.
Yeah, because I was very fast on this part, so I should have taken more time and maybe skipped other stuff.
Yeah.
But basically, I mean, maybe it can be extended to more general shapes than polygons, but I don't think it's possible to extend to very general shapes because the problem is that you want analytic. The problem is the intersection, in my opinion. You really want analytic expression for the intersections so that you can make this exact computation. If you, let's say, for instance, that instead of, I mean, let's say that the boundary of your, let's say it's like a curvilinear polygon or just some shape, okay, some curve, which is parameterized by some function. But it depends. It's going to depend a lot on this function if you can compute these intersections analytically or not. It's very easy to find a curve where you cannot compute these intersections analytically, but you can probably approximate with a lot of precision. But it's not going to be so easy as this case. This case is very easy, and it still is easy to compute the analytical expression, and at the same time, it gives you a lot of possibility because you can approximate almost any set with this kind of union of polygons. So, for instance, instead of union of polygons, it could be a union of balls that you want to approximate. I think this would work also because you can compute the intersections. But for general shapes, I don't think it works this way.
Yeah, and yeah, thank you.
Yeah, Antoine, Lucas is shooting questions in
the last question. Yeah. So I didn't. I can see when you show the numerical results that, I mean, the covering becomes regular, and so maybe the centers form a lattice. But can you use the optimality? I mean, the derivatives to get optimality conditions and show for a large number of points that it's indeed a lattice, the centers and so on? Can you show some theoretical?
We tried to analyze the optimality condition to see if we could say something about the solution, but we didn't. We had some ideas, but we didn't find anything very conclusive. Although, when you look at the results, you can really see some. Maybe I show the other ones. You can really see some stuff that always happen. For instance, I don't know if you can see very well, but you can see that at the solution, very often you have triple intersections. For instance, here this disk intersect at the same point with the boundary. So it seems like a very natural thing. And also the disks themselves,
singular, no? This is kind of a singular.
Yeah. And in fact, I mean, this looks like this could be a problem for our algorithm because the solution, typically they are singular cases. And because the lattice solution itself is made of disk, which, I mean, this configuration that I excluded, the hexagonal lattice is only made of this kind of figures, and this is a degenerate case. So this means the solution of our problems, they are often degenerate case. So it looks like it could be a problem, but the algorithm works anyway.
Okay.
So and about your last question, this is something that we are studying to show that when the number of balls goes to infinity, then the structure converges to a lattice. I mean, it's quite logical that it does this, but the proof, I think the proof maybe is not so difficult, but there's a few difficulties there.
Okay, nice, very nice.
Okay, so Antoine, Lucas is asking too many questions there. Can you call him and give the answer?
But I don't see this question. Where
the chat
in the chat there is if you see there is a symbol of chat. If you click there, then on the right hand side it will appear the whole discussion.
Okay, sorry. Because I was on another chat just with you, Ravi. I didn't see the other one.
So now if you click on the chat, you will see on the right hand side lots of messages.
Xavier is I think we met when I was in Conception.
Yes. When you were here, you definitely met him. Yes.
Yeah. So
maybe we should meet some other time when you're free, just to talk.
Okay.
Yeah, sure.
But if you want, we can continue with a private conversation to answer these questions.
Now I have a meeting. We have a department meeting. So
yeah, in 15 minutes we have a meeting.
Okay. So should I answer his questions?
You can, sure. We still have a little bit.
Yeah, you can. Sure, yes.
But like in this video.
No, maybe you can. We have to stop it because for the meeting I have to switch on the same platform but another meeting. So we have to stop this meeting here. Maybe you can call Lucas through Skype.
No, you can stop maybe recording, and maybe in 5 minutes you can answer some of the questions because we still have time for the meeting.
Okay.
Yeah.
So let me try to answer his question then.
Yeah, that is possible. Yes. If it is quick, something like 5 minutes, then it's okay.
Yeah.
Okay, so first question is when the number of circles is chosen for covering the polygon, you also set their centers, or the centers are also unknown to be computed. No, the centers, they are also unknown. The center and the radius. The centers and the radius. They are all variables of the optimization problem. Okay, so second question is, did you test any case considering the coverage of two disjoint polygons? Two disjoint polygons apart from each other. If you have two disjoint polygons apart from each other, in this case, I think is not really. It's like you have two separated problems. I think so. It's not really interesting in a way, because you're just going to have one covering for one polygon and another covering for the other one. And there was another question. Did you test any case considering the covering of two? Ah, no, this was the same question. Okay.
Yeah.
So I think I
Yeah.
answered all the questions, right?
Yeah. Yeah, Lucas, it's okay. Okay. Yeah. So he is fine with it. So thanks again, Antoine, for the talk. It was really interesting for me. At least it was fantastic.
Antoine, which days are you free in the week, more or less? Like, so
These days I'm quite free, not all the time, but I don't have lectures, so I'm quite available. So I mean, from time to time, of course, I have meetings and stuff like this, but basically, more or less any time. But I mean, I'm quite flexible, I'd say. Yeah.
Okay.
So you want to organize a meeting?
Just to have a chat and maybe
Sure.
maybe next Thursday around, not in the lecture time, but maybe in the morning.
Next Thursday then, or Tuesday?
Thursday.
Thursday, yeah. Okay.
Actually, next week I'm quite free also because we have a small break in the. So I can be
yeah. Next week is a good week.
Yeah.
Okay.
We will write a mail and fix a time then.
Yeah, send me an email. For me, Thursday in general is good. I don't have I don't have many things.
Okay.
So you just send me an email and we can just decide the time.
Okay.
Okay.
Okay. Take care.
Are you at home now or at the university?
Yeah. Still at home. Still work from home.
Yeah, me too. Can you see the back? I'm in my son's room where he sleeps.
No, I can't see your.
If you can, if you stop sharing, then it will be visible.
Ah, okay, I see.